All right. Okay, thank you very much, everyone, and thank you for the invitation to the workshop organizers. I hope everyone's doing well. So I'm going to be speaking about some of the work that we've done on stereotypical biases with focus on gender bias. And I hope I'll finish on the 40-minute time, although I was planning to cut a bit of my slides short this morning, but I had miscalculated the time difference. I thought I had another hour. So I'll be doing some real-time slide cutting, removing some of my slides during the talk to be able to finish on time. So I hope you'll excuse that. So before I begin, I'd like to have a shout out to my colleagues and students who do most, if not all, of the work that I'm going to present today. So I'll start with this broader kind of topic, which has been more and more discussed now within AI systems. This idea of designing AI systems without consciousness for diversity. So if you build a system based on data that lacks diversity and is biased, and then you use techniques that lack sensitivity to diversity, then what you should expect is to have outcomes that are not sensitive to diversity and will exhibit more bias. That's an obvious outcome. If you build a system that uses biased data, uses AI techniques that are not sensitive to diversity, then what would you expect? It's natural that the outcomes will lack diversity and have a lot of bias in them. So we need to kind of systematically think about these issues of bias and diversity when designing AI systems, and specifically in this context that we're talking about, search systems. So I'll begin with, probably most of us have already seen this, but I thought it's a good segue to the things that I'm going to mention. The natural language processing community has explored this issue of biases quite a bit for a few years now. For instance, this paper from NACL 2019, where they investigated issue of race and religion. So they created these word analogies based on Reddit data. And as you can see, they had Black, Caucasian, and Asian, and they wanted to find adjectives that would describe each of these races. So for instance, Caucasian, it'll associate with serviceman and hillbilly. With Asian, it'll associate with suburban and laborer. For Black, it would associate with landowner and homelessness. So a clear bias in how the language model would actually create those analogies. In terms of religious analogies, for Jews, Christians, and Muslims, for Christians, it'll associate with familial and intellectual. For Muslim, it'll associate with uneducated and powerless, and with Jews, it'll associate with greedy. So again, as you can see, a clear biased model trained based on Reddit data. There is also a paper from EMNLP 2019 looking at gender biases, and they used GPT-2 to complete some prompts. For instance, they had the man worked as and also had the woman worked at, and they completed these sentences based on GPT-2. And what they got for the man worked as was a car salesman at the local Walmart. And as opposed to what they got for women, the woman worked as a prostitute under the name of Haria. So again, the language model is picking up on some undesirable issues from the underlying data. So more recently, there's been quite comprehensive reviews of the literature on gender bias within natural language processing. For instance, this paper from ACL covers very nice examples of how biases, gender bias specifically, exhibit themselves in natural language processing tasks, for instance, within machine translation, caption generation, and so on. And they provide very nice examples as well. There's a more recent survey on gender bias in NLP, and they take this a step further by providing also a survey on methods for kind of countering these types of biases. And they categorize these methods broadly into data manipulation methods and methodological adjustment methods. In the data manipulation methods, they talk about ways in which biased training data can be fixed before systems are trained. And then in the methodological adjustment, they talk about how AI training methods can be kind of adjusted in order to be conscious of bias. And in my talk and in the few types of sample work that I'm going to present, I'm going to be talking both about data manipulation work as well as methodological adjustment methods in IR. So before I start with this more specific technical topics, I'd like to begin by this kind of philosophical idea that some people raise, and this is the issue of if there are biases, it's coming from the underlying societal processes that we humans are involved with. And so if you're going to remove these biases, you should probably solve the problem from the root and try to remove these types of biases from society. And eventually, if that happens, then the data that's generated will be unbiased, and therefore AI systems will be unbiased as well. And that argument is not without merits. Obviously, we need to be working more and more on societal biases and so on. But I think addressing issues of bias, things like gender bias, at an algorithmic level is also useful, because sometimes it's easier to fix a biased algorithm to try to fix a biased human or a biased group of people. So you would get results much faster. And at the same time, algorithms that are biased will reach a large population of people, far larger than any single individual. So I think we should be cognizant of both aspects of this, both working on bias at a societal level as well as an algorithmic level. So what do we need to do to address this issue of algorithmic bias? And obviously, if you want to do anything computational, the first thing you need to do is kind of come up with a quantitative way of measuring, right? So so what I'm going to be talking first is what the literature has been using to quantify gender biases in IR systems, and then base my talk on the way that quantitative measures of bias have been used. And then hopefully at the end of my talk, I'll talk a little bit about why I think we need to reconsider these metrics. So one of the earlier works in IR that looked at gender stereotype was the work by Fabrice, and they looked at this idea of genderedness of a ranked list. So, for instance, if you have an ad hoc retrieval method, it'll give you a list of documents, and you want to know how biased this ranked list of document is towards a certain gender. So they define a certain function called GQ of DK, which shows the degree of genderedness of document DK for a given query, like query Q. And they define this genderedness of a ranked list like an NDCG metric. where they would change the relevance to genderedness. And I'll talk about how this genderedness is typically computed within the literature. The work by Rekabsaz and their colleague introduces this metric called the rank bias. And they also have this function, magnitude of DI for a certain gender. Here again, if you have a document DI, the mag function, the magnitude function will measure the magnitude of relevance of this document towards a certain gender. And then they average over all the documents in the list, and then they subtract the inclination towards male minus inclination towards female, and they take this as a measure of bias in a list, in a ranked list of documents. And then they also expand this idea based on, they call it an average rank bias, which is inspired by an earlier work from the HCI field, which is again very similar to the metrics that we have in IR, things like MRR. It computes the same thing as rank bias, but it now averages over different ranks. So, you know, what is the bias at rank 1, at rank 2, at rank 3, and then average over all of those biases, measured biases. Again, another more recent from ECIR2021 metric that, unlike the other ones which measure a degree of unbias, unfairness, here they measure fairness. So it's again very similar to the previous metrics, but rather instead of having a magnitude function or a genderedness function, there is a weight function that measures how fair a document is, and the concept of fairness is defined as a similar degree of genderedness within the document. So if you have two documents, kind of simplifying the concept here, if you have a document that has the same amount of inclination towards male as it has towards female gender, then you would call that document a fair document. So all of these metrics and some others are all based on this quantification of bias. So if I go back, for instance, here, this relies on this magnitude function. The previous one also relies on the magnitude function. This one relies on the G function, the genderedness function. So they all need some form of a quantification of genderedness. And so what has been proposed, one of the ways it's been proposed, is to look at a list of gender terms, a predefined list of gender terms, to kind of define genderedness. So for instance, this is a list of male gender words here, and there's a list of female gender terms. And so, for instance, in the magnitude function, in RAB and ARIB metrics, they count, for instance, the frequency of these male-related keywords that appear in a document versus the frequency of the word, the female words. Or they would just look at the Boolean presence of these words in a document or not. So they can be different variations, like a Boolean form or a term frequency form. So in essence, just to summarize this, when looking at a ranked list of documents, genderedness of each of those documents really depends on whether or how many of these words are appearing in the documents in that list. And I'll talk about some of the issues that we think there are with this type of measurement of bias towards the end of my talk. But let's agree that we're going to just focus on these metrics and assume that these metrics are good metrics for now, although we know there are some issues with that. So one of the earlier works that raised this issue of gender bias was by Rekabsaz and their colleague, who talk about whether neural ranking models actually intensify biases. And as you can see, they work based on the two metrics that I just introduced, RAB and ARAB. And they show that for different retrieval methods ranging from BM25 to rankers based on birth, that there is the measurement of the degree of bias observed in the retrieved list of results is different, where BM25, for instance, here is showing the least amount of gender bias, whereas birth-based retriever is showing the highest amount of bias towards the male gender. And the kind of takeaway from their paper was that if you have neural models that are trying to do retrieval, the amount of gender bias that you observe from them actually gets increased compared to more traditional retrieval models. So within our group, we set out to look into why could that be the case? Why do we see an intensification of gender bias in neural rankers? So immediately when you think of neural rankers, there's a couple of things that come to your mind. And as I mentioned before, it could be due to the data it's trained on. It could be due to the method that's being used to train and so on. So we developed this first hypothesis that maybe some of those biases that you're seeing is because of the training data that's being used. Because if you compare BM25, let's say, to a birth-based re-ranker, for instance, BM25 is not being trained, it's just retrieving documents based on frequency associations between the query space and the document space, but the neural ranker is being trained based on a training set. So could some of the biases be due to the training set? And so the training set, as you all know, that we use for training rankers is the relevance judgment. So we looked into MS Marco relevant judgments, and I'm just going to show you a few examples of query and relevant document pairs. For instance, within MS Marco, you have a query, how important is governor? And the documents that's associated with it and labeled as relevant assumes implicitly that a governor can only be a male, because it's referring to the governor with male pronouns only. So if you have a model that's been training on this, it will associate, although not directly instructed to do so, but it'll associate the term governor with these male pronouns. Another example of it is a query related to US president. And again, the answer implicitly assumes that the president is a male, and therefore, again, the concepts of presidency will be learned to be associated with the male gender. And as we know, within the US Constitution, the US president does not necessarily need to be a male. Neither does a governor, actually. Another example, how much to rent a room in a house, that's a query from MS Marco, and the associated relevant document, again, assumes that the person looking to rent a room is a male figure. And it just uses these male pronouns to refer to the person who's planning to rent a room, right? So again, it kind of, any neural model that you train will pick up on these nuances and probably associate the process of renting a room with a male gender. So we looked into a bit more systematically into MS Marco. So what we wanted to do was to compare the documents retrieved for queries that are affiliated with different genders, and see whether there's any systematic difference. There's about 500,000 queries in MS Marco, so it's very hard to do it manually. So what we did was we fine-tuned a birth classifier based on the data that was released by a ECIR2022 paper that provided a list of female queries and male queries. So that data set has 1,700 neutral queries, 700 female queries, and 1,200 male queries. So we fine-tuned a birth classifier so that when you give it a query, it'll classify it into male, female, and neutral. And so our classifier has an accuracy of around 85%. on a held out set on the same training set. So I'll give you some of the examples of what query gender looks like. For instance, if you have, can you take naproxen during pregnancy, it'll label this as a female-related query. On the other hand, if you have something like foods that can prevent prostate cancer, it'll label this as a male query. And things like average percentage of accepted scholarships, it'll assign it a neutral, as a neutral query, and it's not affiliated with any genders. So what I'm going to show you now is based on the MS Marco dev set, and only on those queries that have at least one relevant document. So that kind of sums up to 51,000, 52,000-ish queries. So what we wanted to do was look into these underlying processes behind association between queries and relevant documents. So we used Luke, which captures kind of psychological characteristics of textual content. But the first question we wanted to answer was, is Luke a reliable tool for what we're trying to do? So what we did was we took the documents that are related to each query, ran it through Luke, and took the gender affiliation characteristic that Luke provides for each document. So Luke has this metric called gender affiliation, and we measured that for each of the documents. So the expectation is if a document is associated with a certain query that comes from a certain gender, then that document is more likely to be affiliated with that gender as well. That's an expected outcome. So for all the female queries and all the male queries, we measure gender affiliation of the associated documents within the relevance judgment based on Luke. And as you can see, in about 80% of the time for female queries, the documents come out to be female documents based on Luke as well, and similarly for male document queries. So we kind of concluded that Luke is a reliable toolkit to be used for this case. And so what we did was we measured these different psychological characteristics over MS Marco dataset the way I explained it. So we have 3 types of queries: female queries, male queries, and neutral queries. And the expectation is that these processes should be comparable across queries. For instance, one of the cases where they're comparable is positive emotions. So for male queries and female queries, positive emotions expressed within relevance judgment documents affiliated with each gender type query set is comparable. So that's a good outcome. But if you look at other things, you start to see noticeable differences. For instance, in terms of negative emotions, female queries have a higher expression of negative emotions. In terms of anxiety, you see a high degree of anxiety in documents affiliated with queries for the female gender. In terms of anger, it's much larger for male. For sadness, it's much larger for females. If you look into more detailed psychological characteristics, for instance, personal concerns, you'll see that it's again very different how the documents are affiliated with each of these psychological characteristics. So what we concluded there is that obviously the training set that's being used for training the AI models is showing a lot of stereotypical gender biases in it, even if you look from a psychological characteristic perspective. So obviously that's there, but the not so obvious question is, how do you go about addressing some of these stereotypical biases in relevant judgments? And I'll talk about a recent work that we've done on trying to debias some of these large-scale relevance judgment data sets. So we know the relevant judgment data sets can be biased. The objective here is to try to debias these relevant judgment data sets. So if you think about the way a relevant judgment data set works, is there's a bunch of queries and a list of relevant documents for each of those queries. So if you want to try, one of the ways to try to debias these data sets is to have a data set where for each query, let's say affiliated with a male gender, you would have a corresponding female query that would exhibit similar characteristics. And if you have a data set like that, then you've managed to systematically balance, if you will, your relevant judgment collection. So I'll give you some examples. So if I have a query that says, what are the primary male sex hormones? I would put in a comparable query, like which hormone is required to regulate uterine cycle. So if I'm able to systematically build a collection that has these comparable queries in it, then I've managed to at least try to minimize biases. But with large relevant judgment collections, it's pretty much impossible to manually create such balanced pairs of queries within your collection. So what we proposed was that you can probably create synthetic queries, comparable queries, to try to balance and debias your collection. And what we propose is, for any queries within, let's say, MS Marco, that you find affiliated, let's say, with a male gender, then you'll synthetically create a query affiliated with a female gender that has comparable characteristics. And the way we propose to do that is to use these methods, something like a doc-defined query, which generates queries from documents. So what we propose is that for, let's say you have a query that's a male query and it has a relevant document, you would find another document that's very, very similar in nature and also psychological characteristics to your initial document. But the only difference is that that document is affiliated with a female gender, for instance. And then you would generate a query for that document, and now you have a pair of queries that have documents that are comparable in terms of their psychological characteristics. And that's how you can generate a lot of query document pairs. So now you can see that it's that you can now generate a lot of query document pairs that are comparable, right? Because you can go, let's say you have 200,000 male queries, just for the sake of argument, that number is not accurate. In MS Marco, you can actually go through all the documents in MS Marco, identify the ones that are female documents, and for each of the male queries, you would pick out the document that's affiliated with a female gender, has comparable psychological characteristics to a document associated with a male query, and you would pair them up. And this way, and then you generate a query for that document. And this way, you have pairs of comparable relevant documents and pairs of relevant queries from different genders. So what we did was we generated queries the way I explained, and obviously because queries are extracted from documents, then immediately we have relevant judgment information for those queries as well. It's quite obvious the relevant document for a query is the document that query was generated for. So we created a whole bunch of these query document pairs, and we added them to the original MS Marco set. But we didn't add all of it at the same time. We added it gradually. So we added about equivalent to the 5% of MS Marco queries that we had generated, and then we added 15%, 25%, and 35%. So we gradually added those. And we measured how adding these synthetic query document pairs actually impacts MRR. So the original data set from trained based on the original MS Marco dev set gives us about 0.3 MRR. And if you add these synthetic queries and document pairs, the expectation is if you add a lot of them, then the performance of your ranker will drop. And that's what we also observe. But what we found is up to about 25%, adding 25%, you get a drop of from 3080 to 3002. It's about 2.5% drop in MRR, but that drop is not statistically significant. But if you add about 35% of those, then your drop will be about 6%, and that is significant. So we added these data until the performance became significantly different. So the one that we used was about 25%. So now our training data consists of the original MS Marco data plus 25% of these synthetic query document pairs that we generated. And this is what we found was that if you compare the differences based on the look characteristic that I showed you earlier, the difference between the performance of the model is not statistically significant in terms of MRR, and at the same time you get a noticeable reduction in the difference between the look characteristics of your gendered queries. So comparing female queries to male queries, for instance, in terms of effective processes, the difference, the undesirable difference reduces by 36%, on cognitive processes by 8%, and so on. So you can actually reduce these biases by just adding these synthetic query document pairs without sacrificing your performance, your retrieval effectiveness. There's also two query sets from ECIR2020 and 2021, which are kind of so-called neutral queries, where you would expect that bias, there shouldn't be bias between male and female queries. And what we show is by creating this debiasing strategy, adding queries to your original training set, you can actually reduce measures of bias. For instance, the term frequency, ARIB metric, and the Boolean version of it, you can reduce those consistently, both on the first query set and the second query set. So it's quite effective. You can actually create, so what we find is it is possible to create these automatic debiasing methods. One of the concerns is that, you know, if you change your training set, you'll hit retrieval effectiveness, and we find that that doesn't necessarily need to happen. And then you can actually debias some of these very large scale relevance judgment collections to actually more fairly represent gender, for instance. So the other aspect that I mentioned is how do you address biases now within retrieval methods themselves, not the data sets. And I'll talk about a few of these. But before I continue, how much more time, how am I doing with time? Am I already over, or?
You still have around 8 minutes.
8?
8 minutes, yes.
Okay, so I'll have to go faster. So I'll talk about, and then I'll do some real-time editing of my slides. I'll skip a whole bunch of them, and I'll just talk about maybe 1 or 2 more. So looking at how to address these stereotypical biases within the methods, retrieval methods, how can you have a neural ranker, how can you make it a fair neural ranker that's aware of gender biases? So what we define, obviously, as a fair ranker, let me define what a fair ranker is. A fair ranker, in our work, we define it as one that maintains same level of retrieval effectiveness while minimizing biases, right? So if you look at a typical loss function, like a hinge loss function, it has 2 components mainly. It's trying to maximize the distance of the query to an irrelevant document, and at the same time minimize the distance between the query and a relevant document. So that's a typical a loss function used in rankers. Now, what we propose is that if you want to make your loss function bias aware, then maybe you can incorporate this notion of bias within your loss function. So if you have a relevant document, but it's a relevant document that's showing a lot of undesirable stereotypical gender biases, then you should probably penalize that relevance. At the same time, in a different way, if you have two documents that are irrelevant, the one that's the worst irrelevant document is the one that's both irrelevant and also showing a lot of stereotypical biases. So you should penalize the document that's irrelevant and showing stereotypical biases more. So that's the whole idea. It's quite simple. And then when we look at these bias performance or retrieval effectiveness trade-off, there's a few considerations to be had. The first issue that is these large-scale relevant judgment like MS Marco, they're very sparse. It's typically around one relevant document per query. So if you start penalizing relevant documents that we're proposing here, then because there's only one relevant document per query, and you penalize that one document, then you will end up with your loss function not being able to learn the concept of relevance. So that's the first issue. The second issue is in border cases where relevant documents and irrelevant documents look very similar to each other. Then in those cases, if you penalize the relevant document with due to the stereotypical biases that it's exhibiting, then you will end up with a list that's showing less biased documents, but those documents are irrelevant, which kind of defeats the purpose of information retrieval. So what we're proposing here is to relax those conditions that we put, and we said, when you're learning the concept of relevance, you can forego the concept of bias, but when you're learning what is irrelevant, you should strictly learn what is irrelevant and what is biased. So that's what we introduce. So I'm just going a bit faster here to show you some experimental results, and we compare with the work by Rekapsas from ECIR2021, which is a very nice paper on trying to address some of these gender stereotypical biases by creating an adversarial training method over BERT. But what we show is that even with a simple way, you don't have to overcomplicate the method to address some of these issues. You can actually get very nice reduction in differences between genders, with the expression of gender biases. So for instance, our method on BERT Tiny, if you train it on BERT Tiny, it'll actually increase a bit on MRR. On BERT Mini, it reduces a bit on MRR on BERT Mini, but if you compare it with ADVBERT, the degree of impact that ADVBERT has on performance is much more. But our quite simple method of kind of incorporating bias measurements into a loss function actually performs quite well on MRR, and we contextualize that with the other objective of reducing of biases. So as you can see, our method kind of consistently reduces biases that are exhibited within the ranked list. Sometimes it's not as much as ADVBERT is able to do. For instance, in this case, our method reduces by 28%, whereas ADVBERT reduces by about 45%. But we note that there's a trade-off, right? So you want a method that has good retrieval effectiveness also reduces your gender bias. And so we think that a simple method like ours is able to perform better compared to a very nice theoretically founded ADVBERT model, because ADVBERT kind of hits your MRR. So you don't have a method that performs as well on retrieval effectiveness. So I'm going to skip some of these methods, and I'll just point out that we'll talk about, my colleagues will talk about a work we have at ECIR, how to adopt a a very simple method for sampling, negative sampling, that helps reducing bias. And later on at ECIR this year, we'll talk about another method of addressing performance disparities in neural anchors. But for the sake of time here, I'm going to skip these and just talk about the metrics, the bias metrics. So as I mentioned at the beginning of the talk, a lot of the work that we do in this space, different papers, all rely on these measures of gender bias. So we need, because we're a computational field, we need to kind of create a quantitative methods of measuring what gender bias is. But what we found in our work is that sometimes it's hard to interpret what these measures are actually measuring. So I'll talk about these metrics, and I'll end on that note. So if you have a gender bias metric, you need it to be consistent. So what is consistency? If I have two metrics that promise to measure the same thing, then the performance of those two measures need to be correlated. If I apply those two metrics to two different data sets or on the same data set, I need to be seeing correlated outcomes. So what we set out to do was we said, okay, we have a bunch of queries, let's say from the ECIR paper by Rekapsaz. They provide about 1,700 gender neutral queries. If we run these metrics, different gender bias metrics over these, then the performance of these metrics should be correlated because they're promising to measure the same thing. So what we did was we ranked all of these 700 queries, and then ranked them based on the degree of bias that each metric calculates for each of the queries, and we created 4 buckets. So the idea is that for each of those, let's say if I take the NFAIR metric and the TF-ARIB metric and compare them, the expectation is that the queries that are put, let's say, in the 4th bucket by NFAIR are the same queries that are put in the 4th bucket by ARIB, if they're going to be consistent, having a comparable performance in terms of measuring gender bias. What we find is that in the 4th bucket and the 1st bucket, so these are the least biased queries, and these are the highest biased queries, that there's quite a consistency. About 74% here and 71% are consistent. So the queries determined by both metrics are the same. Where we have issues, even on the other ones, like consistency between ARIB and Boolean version of it and the term frequency is quite high, 84%. Where we see the issue is within these borderline queries. Queries that we don't know kind of sit at the middle. There's very little consistency between these metrics. So if something is quite clear in terms of being biased or not biased, then these metrics are quite consistent. But if there's something in the middle, then these metrics become not really consistent with each other. And that's a big issue. If we're reporting papers on how our methods are actually reducing bias, we need to actually be looking at this whole bunch of queries sitting at the middle, because they will significantly impact what we report. The other aspect of it is sensitivity. As I mentioned, most of these metrics rely on a predefined list of gender terms that are used to quantify bias. So, we count how many of these gender bias terms there are, or for instance, what's the frequency of them. And so, the idea is that this is a predefined list. So I could take like 10 words and add them to it, or remove 5 words from it. And the idea is, the measures that we have shouldn't be really sensitive to what set of terms there are, and should be, performing consistently regardless of those terms. And what we find really is that these metrics, as expected, are very sensitive to the type of terms that are used in them. So if you randomly subsample from the initial set, 25%, 50%, and so on, you will see significant changes in how gender bias is captured and reported. And finally, the other issue is, do we understand what underlying psychological characteristics these bias metrics are capturing, because it's important, right? We're quantifying something. Do we know what our quantification is actually capturing? So we looked at the correlation between these bias measures, NFAIR, ARIB, the Boolean version, the term frequency version, with the psychological characteristics exhibited by Luke. And what we find is that the first psychological characteristics that all of these metrics are correlated with is the male reference. The second one for the ARIB is the female reference, but for the NFAIR, it becomes past focus, present focus, and so on. So the female gender is not even on the list here for NFAIR. For these ones, there is reference to both genders, but again, it goes into this concept of time, temporality. So, so what we find is that these metrics are more inclined towards the male gender. And for some reason, these metrics are confusing the concept of time with the concept of gender. So first of all, the measurements that we're doing and reporting in our papers are primarily measuring things based affiliated with the male gender. And then we're actually reporting things that are not even related to gender, things like time. So I'll conclude here my talk with two issues of how we're treating gender bias. The issue of this concept of term-based measurement of gender, where we take a document, we count how many gender terms there is in that document, obviously will create this issue where the semantics of the document is not the way we think it is. For instance, in this first example, female CEO says women shouldn't be present because of different hormones, biblical reasoning. Obviously, this document is saying females shouldn't be presidents. But if we take our frequency-based measures, it'll say, hey, there's more female-related words in here, therefore this is a bias towards females. Or the other example is the next president should not be a man. Our metrics currently would say this is a document inclined towards male gender, whereas it is not. So we need a bit more of a deep treatment of the concept of gender. And then the other issue is this idea of gender binarism. Most of the data sets that we have, except one, consider gender to be this binary form of gender, which is either male or female, and don't treat other types of gender. And it's not as easy, I understand, to capture a wide spectrum, but I think we need to start thinking as a community on how we can address a wider range of gender identities. So I'll conclude with saying that unfortunately, as our work has shown and other people have already shown, is that these stereotypical biases can be intensified at scale in information retrieval systems. The intensification can be due to, for instance, inherently yet unintentional bias relevant judgment collections, and then biased rankers that optimize for relevance only and don't consider the concept of fairness necessarily. The good news is that in some of our work and some other researcher was in the field, that it's possible to debias relevant judgment collections at scale and also introduce ways of debiasing neural rankers for better unbiased results, at the same time not sacrificing retrieval effectiveness. So thank you very much, and my apologies if I went too much over time here.